Okay, our quick look at the calendar. So we have finished 4 classes on apportionment. We're done with apportionment. Today we start a new topic. The new topic today begins with sequences, which are just lists of numbers, and then we will use our knowledge that we develop of sequences to talk about some more interesting things like population growth, and then something really cool called the Fibonacci numbers. So we are halfway through the material for test number 2. 4 classes on apportionment are behind us. 4 classes on this new stuff are ahead of us. Then we have our review day. Test number 2 is on November 18. Also on the calendar, the apportionment project is due right here, November the 4th, which is 1 week from today. All right. So far, I have 3 people that have already completed and submitted that project, which is great. I know some other folks are working on it. I know some folks haven't started it yet. The project, to be honest, is not all that hard once you understand how to use the commands inside of Excel or Calc, which is the open office version of Excel. But that can be really frustrating. If you don't have the syntax right, you get all these errors, and sometimes it's hard to diagnose what those errors are. So again, I encourage you not to wait until the last minute, because if you do, you might not have time to ask the questions. Could be simple answers to your questions, but you need time to ask them, okay? Questions on the calendar. Okay, so here we are on page 22. We'll start at the top, and we'll go to Jeremy. Oh, sorry, 1 second before you jump in. I'm adding something to your homework assignment. So if you want, maybe real quick, we can go to whatever page this one is here. It says 25. So on page 25, there's a worksheet, and that worksheet continues on to the next page. And then you'll find the answers. That worksheet is now part of your homework, both pages 25 and 26. Everybody see it? Make a note someplace. You can go to the homework assignment, which is a page after if you want to.
So that we would staple to our homework?
You don't need to rip it out. You can just write your answers down and
okay.
On the loose leaf that you have. That's fine. So, so I guess I'll add right here. The homework assignment is also pages, was it 25 and 26?
Yeah.
In this packet. Okay. Everybody understand the additional homework assignment? It's not listed there, so you got to make a note of it somewhere so you'll remember. Okay, so if we're ready, we'll go back to page 22 and Jeremy. Let's pause 1 second. Everybody see the first cake? This is an overhead view of the cake. 1 cut. How many pieces? 2. Great. Okay. How many cuts are there in the second cake? You answered the next question. So there are 2 cuts in this cake. And how many pieces are there? 4. Okay. The next cake has how many cuts? 3. Don't count the pieces just yet. In the next cake, how many cuts? 4. Ultimately, what I'd really like for you guys to be able to tell me is if you have 10 cuts, how many pieces of cake you will have. But can you imagine trying to draw 10 lines and then counting all the little teeny tiny pieces of cake? It would be challenging. So better than that is to fill in this table. When we have 1 cut, there were 2 pieces. That was the first picture. I want you guys to count and fill in the next 3 boxes, and then see if you can figure out what that pattern is and fill in the rest of that table. So work with your neighbors, and we'll come back together in just a minute. Okay, so we've got a bunch of numbers filled in the table. What was the basic rule that people found to fill in the numbers in the table? Alicia?
Well, like from 1 to 2, you want it by 2, and then from 2 to 3, you want it by 3. Added. So 4, 5, 6,
Everybody see that pattern? We went up by 2 or 3 or 4. I've left this one blank over here, but I guess that means the pattern would probably continue going this way. What should it be down here? +1. So what number is in here? It's also a 1. Okay, that seems good. And does that make sense? If you make 0 cuts, you'll have 1 piece of cake?
Yeah.
Yeah, you'll have the whole cake. All right. So this is a nice mathematical thing in that it would be a whole lot harder to actually draw a circle with 10 cuts and then count all the pieces. You might miss some, your lines might overlap, like some of the pieces could be really small. Like in here, you can see the pieces are kind of getting smaller and they'd be really small if you had 10 cuts. And it's nice to recognize the pattern here. And I'll say even more, what if I wanted to know, let's suppose that I was standing on, let's say I had, here I'll extend the table up here. Suppose that this is the number 20 and I'll just make up, I don't know what the number is that goes here, but I'll make up 150. It's bigger than that, but I'm just making it up. 20 cuts, 150 pieces. How would you find the next number? Why is it at 11? Yeah, so that strategy would be sound, add 11, except I skipped a bunch of numbers. I jumped from the 10th number to the 20th number. So I think Casey's dancing around the right thing. Like you guys just knew the pattern because you had all the previous numbers. But what if I only gave you one number in the middle of the table? And so then you don't have all these things. Yeah, let's figure out what we have to add. So if we take a look here, this guy, this +4, I see up here. And in a different color, I see this 3 is down here. So apparently going from the second number to the third number, you add 3, which is that number. So going from the 20th to the 21st, you add 21. And so, so it's nice to really kind of look and really understand, is there a way to get this next number only knowing the previous number, as opposed to knowing all 10 of the previous numbers? Okay, so let's keep going down here, and we'll go back to Stephen, the sequence. Finite. Okay, so the finite just means that there's an ending point, right? A start and an end. In this case, there's 3 numbers in this list, the sequence. Infinite means it goes forever. That dot, dot, dot contains a lot of information. Okay, we're going around to Casey. The numbers. Wait, where are you? Okay, so the pattern in the second example is a lot of even numbers, right? So there's a definite pattern there. Okay, so now let's look at the notation, and we'll go to Griffin. Okay, so the most important thing that Griffin just read to us is that the subscript tells you where to look. Subscript tells you where to look. So capital A is just the name of this list of numbers. That's kind of arbitrary, but 3 is the important thing. When I say A3, I'm saying go to the list of numbers called A, which is these even, and find the third number in that list. So A3 is the third number in, 1, 2, 3, it's 6. A3 is 6. Everybody see it? Okay, so let's answer this next question. What is A5, which would be the 5th number in that list, which actually isn't written down yet? Kate? Kate says 10. Agree? The 5th number in that list is 10. So it is 10. So the subscript tells you where to look. Okay, let's see if we can fill in some information here. A2 and A1. All right, what is A2, which is the second number in this list? It's 4. What is A1? Is 2. And now we're filling in the blank to make a true equation. What number do I have to add to make it true? I add 2. Can you guys write that same kind of blue thing for the other blanks, and then we'll come back together. What goes in each of these blanks here?
2.
2. Okay, so now I'm going to write down this this pattern in English, and then we're going to write it in the symbols. These last 2 blanks are the tough ones, although one of them is easy. Which one is easy? All right, it's definitely +2, but what goes in that other blank requires a little bit more work. So here's what we're going to say. What this says, this equation right here says, is that if you want to get the 5th, you know, this isn't even worth writing. Does anybody know what goes in this blank here? Just A, AX, AN. Barb, you're holding out on us. Barb says this. Barb is right. So here's what this thing says in plain English. Here's what it says. A sub n is just some generic term. So we're just going to say to get the current term. So A sub n is just going to be our name for the current term, but it's general. So that n is just a variable for us. What do we do? Well, we're taking something and adding to. That's the easy part. But in plain English, what's a good name for A sub n minus 1? I want to know what's a good name for A sub n minus 1. I'm calling A sub n the current term. So I'm standing at some, what is it? The former term or the previous term. That's what this says. It says if you are sitting at A sub n, some arbitrary spot, you need to look at the spot one before, one less than the one that you're sitting on right now. So that's our way of saying to get the current term, you take the previous term and add 2. So that's what we're right here. Take the previous term and add 2. So maybe this is worth writing over here. We're going to say A sub n. We're just going to call that the current term. And then A sub n minus 1 is called the previous term. Because the previous term is just one before the current term. So if you're sitting on an n and you want to go one before, it's just n minus 1. What if I gave you something like this? A sub n minus 2 is go back 2 terms. You're standing at the current term, go 2 terms before. What if I said a sub n plus 1? That means go forward a term, right? So n is just where we are sitting right now. That's our current landmark. If it's n minus 1, you go back a term. N plus 1, you go forward a term, okay? So there's nothing really challenging about the pattern right there. The new thing for you guys that you're going to have to grapple with is the notation. It's this idea of a sub n, and what does it represent, and a sub n minus 1, and what does it represent? That's the hard part for you right now. Okay, let's keep going. Griffin, you already read. Sam, this is? Okay, so that's exactly what we had. In order to get the current term, we had to use the previous term, right? We added 2 to the previous term. Anybody know what the beginning of this word means? R-E-C-U-R? What does that mean? It means to repeat, to happen a lot, happen over and over again. So the pattern here is you take the previous term and you add 2 over and over and over again. So that's where the word recursive comes from. Okay, moving down here, same list of numbers, 2, 4, 6, 8, etc. Let's take a look at this first one. A sub 1 is equal to, how much was A sub 1? Is 2. What number can I fill in the blank in order to, all right, so 2 is really 2 times 1, right? what is a sub 2 in the list? Is 4, which is really 2 times what number? It's 2 times 2. Can you guys fill in the other blanks? You might already see the pattern, but pretend that you don't. Just do some calculations to fill in those next 2 blanks. A sub 3 is 2 times 3. Yes, it is. A sub 4 is 2 times 4. And now we're going to write the general rule. A sub n is 2 times n. Plain old n. Not a sub n minus 1. Not a anything. Just plain old n. Let's see if we see that pattern here. A sub 3 was really 2 times 3, right? That 3 ends up getting copied in the blank. A sub 4 is 2 times 4. A sub n is 2 times n. Okay, this is it's the same list of numbers, but this is a very different way to describe the rule. The previous rule says, okay, if you want to get the next number, you got to add 2 to the number that you were just on. But this one doesn't say anything about the number you were just on. It says just take 2 and multiply it by n, whatever n is. So for example, suppose that I asked you to find A100, the 100th number in this list. It's just plain 200 because this rule says you multiply 2 by the subscript. So this is just plain 2 times 100 or 200. It was really easy to find the 100th number in the list using the rule we just wrote. But to use the previous rule, in order to get the 100th number in the list, what do you need to know first? You need the number before. You need to know the 99th number in the list. But in order to use that rule, how would you get the 99th number in the list? You'd need to know the 98th number in the list. You'd need to know all the numbers up until the 100th one. Right now we have A5 there's a rule up here written for A5. And so you could say, okay, if I want to get to A5, I add 2. So how much is the next number? It's 10. And then if I want to get the next number, it's 12. And then 14 and 16 and 18. And you can keep going, and eventually you'll find the 100th number is actually 200. But gosh, I'd really rather use this rule than the recursive rule. Okay, we'll go back to Mary. Last paragraph here. At the that make sense? All we needed to know was that n was 100, and then we could just zip to the answer. That's an explicit rule. Okay, so we're going to play Guess My Rule. So it's a good party game. So here's a table of values. We have some n's up there, and then some numbers down here in the bottom. This sequence is not called A. What is this sequence called? S. It's just an arbitrary letter. So don't get hung up on the A or the S. The subscript is the important thing. Okay, so what I would like us to do is calculate S sub 5. So first we got to figure out what the rule is here. So how do I go from this number to this number? We add 1.5, and then here, add 1.5, and here, add 1.5. Okay, that's pretty compelling that we have found the pattern. So we add 1.5 and we get 7.5. Can I ask, instead of just writing 7.5, that you actually write S sub 5 equals, just to practice with this new notation? And then the next one should say S sub 0 equals, what does it equal? It is 0, just working our way backwards. All right, subtracting 1.5, so we'll go to the left. Okay, so let's talk about this recursive rule. I'm going to first write it in English, and then we're going to write it in the new symbols. Okay, to get the current term, what do? Add 1.5 to what? The previous term, or the term before it. Okay, what's our generic name for the current term? It is now S sub n. It was A sub n. We'll use the n every time. The subscript thing will always be n in general, but the other letter makes no difference. Okay, to get the current term, we're supposed to add 1.5. So 1.5 plus, and then what's our notation for the previous term? Sn minus 1. That's it. Any questions on the recursive rule? Okay, that is the recursive rule right there. Technically, we need one other piece of information. I'm going to write it over here. I'm going to say S1 equals, what is S1 looking at the table? 1.5. We need both of those pieces of information. The recursive rule tells you how to get the next number once you know the previous number. But you got to have a starting number. Like at some point, you need to have a start. And so we have to write down some starting number coupled with the recursive rule. Okay, the explicit rule. Let's think about this. So we're adding 1.5 every time. That helps us not at all in terms of finding the explicit rule, because the explicit rule doesn't allow you to look at the previous answer. The only thing we're allowed to look at for the explicit rule is the top row. You can't look at the neighbors. So for the recursive rule, we're going to do this, like going side to side business. But if I want to think about the explicit rule, I need to come up with a relationship between the numbers that are vertical of each other. So we need a rule that takes 4 and sends it to 6. And the same rule hopefully will send 3 to 4.5, and we'll send 2 to 3. Can anybody tell me what to do with the top number to get the bottom number? Divide it in half. So if we take 4 and divide it in half. Oh, so you take 4 and you divide it in half, and then you add it to the 4. Well, let's see if that works. So Nicole says take 4, cut it in half. What do we get? We get 2. And then you take this guy and you add it to the 4 that we already had. 6. Okay, it is 6. Let's see if that works all the time. How about in here? Let's take this guy, cut it in half. What do we get? 1. Nicole says you add that to the number that you start with in the top row. Does it work? It does. Yeah, that rule works. Casey? Yeah, so this is going to be a more direct way of the rule that Nicole is saying here. It turns out the bottom row is always 1.5 times the top row. If you don't see that, what you might do on your calculator is just take 6 and divide it by 4, 4.5 and divide it by 3, 3 divided by 2. And when you type each of those in on your calculator, you're going to get 1.5 every time. And that's pretty convincing evidence that, oh yeah, the bottom number is 1.5 times the top. So let's see here. Our formula for this guy, Sn equals, Casey says 1.5 times n. 1.5 times n. Okay. So I'll say this again. To get the recursive rule, you're looking left and right. How do you get from 1.5 to 3, from 3 to 4.5, from 4.5 to 6? That's the recursive idea when you look at the neighbors, look at the previous term. But if you want an explicit rule, you don't get to look at the previous terms at all. You need to just go from the top row to the bottom row and come up with some formula. Okay, let's move on. Where are we now? Brandon? S is a special. Okay, so that's a special one right up there. If you have to keep adding the same number, like 1.5 in this case, it's called an arithmetic sequence. Okay, let's take a look at this next set of numbers. And we want to find G5 and G0. So what rule will get you from 5 to 10, but also from 10 to 20 and 20 to 40? Yeah, it's not an addition thing anymore. If it were addition, what number could you add to 5 to get to 10? We could add 5 here, but then to get from 10 to 20 is a 10, and then 20 to 40 is a 20. Is this an arithmetic sequence? It's not, because you don't have a consistent number that you add every time. But in this case, if we multiply by 2, and then if we multiply by 2, and then if we multiply by 2, so that's our consistent rule. It's a different kind of sequence, where you just keep multiplying by the same number. So G5 is 80. And then G0, it's not 0. It's 2.5. Yeah, if moving to the right, the rule is multiply by 2, then moving to the left, it better be divide by 2. So you can take 5 and divide it by 2, or you can write it as a decimal. Okay, let's think about the recursive rule. I want to write English before I write symbols. Current term equals, in English, term before depends on how you write the equation. I think the way we've written it is correct. So to get the current term, you take the term before and you multiply by 2, yes? So in symbols, what's our name for the current term here? Gn equals it's good. 2 times the previous term. Sam, is that all right? What do you think of those symbols? You see where the equation came from? Okay. I mentioned before, you always have to write one other thing when you write the recursive. You got to give me a starting point. Really, any starting point is fine, but the first number in the table is the natural starting point. G1 is 5. Okay, the explicit rule. The explicit rule, you don't get to look left and right. You don't get information about the previous term if you want an explicit rule. So what are we going to circle here to really try to find a different pattern? We'll circle 1 and 5, 2 and 10. That's where we're trying to find a pattern. What can you do to each top number to get the bottom number? This pattern is a lot harder to find. Some rule that's supposed to send 1 to 5, 2 to 10, 3 to 20, and 4 to 40. This is tougher. Okay, so here's what we're going to do. Let's take a look at, okay, so I'm going to look at the number 10, and I'm going to say, okay, I'm going to cheat a little bit. How did I get 10 looking at the previous number? It was really 5 times 2. That's where the 10 came from. So, so 10 was really 5 times 2. So now I'm going to look at the 20. The 20 was really, again, cheating and looking at the previous number. Where did 20 come from? It was 10 times 2, right? But now I'm going to do something really strange. I'm going to replace the 10. See, the times 2 is still going to be there, but I'm going to highlight here, this 10 is about to get rewritten in here. 10 really came from, 10 is 5 times 2, right? So do you guys buy? I mean, I can just change 10 into 5 times 2. It's still equal, right? So 10 is really 5 times 2. We believe that. 20 is really 5 times 2 times 2. We believe that. Okay, let's do this one more time. 40. Why did 40 come from the table initially? It will be, yeah. Casey's already seen the pattern. Why? Looking to just the neighbor, though. Where did 40 come from? Mary says 20 times 2, right? That was our rule. Just take the previous number and multiply by 2. Good. But then instead of 20, so I'll put this times 2 over here, and then I'm gonna replace. Instead of 20, what is 20 really equal to according to what we just wrote? 5 times 2 times 2. Agree? So is this true or false? 40 equals 5 times 2 times 2 times 2. It's true, right? I mean, you can just do the arithmetic if you don't believe it. Okay, so this is heading us towards an explicit rule, because apparently to get a number in this table, you're supposed to always multiply 5 by a certain number of 2's. You multiply by 5, multiply 5 by a bunch of 2's. And how many 2's we're supposed to multiply by? Well, that's still some work to do. This 10 was really G what? What number was it in this table? This was really G2, and this 20 was G3, and 40 over here was G4. When we were finding G4, how many 2's did we need to multiply by? All right, so G4, we had 3 2's. G3, G3 had 2 2's. G2 had 1 2. So there's a pattern there. So let's see if we can write this out. Gn equals. What do we always multiply by in the front? 5. It was always a 5. Times, now how many 2's do we want? Something with n in it. It's n minus 1. When we were looking at G4, how many 2's were there? 3 2's. So apparently the number of 2's is always one less than that subscript. So I'm just going to write this in English, and then we'll write it symbolically. N minus 1 2's, if I can write it that way. That's how many 2's we're supposed to multiply by. So I'm going to erase this part in just a second, but it's supposed to be 2 times 2 times 2. And then I got to fill in the, I don't know how many to put, so I'll just put a dot, dot, dot. But we got to get the right number of 2's. Now, what's the fancy math way to say multiply by 2 times 2 times 2? This is really 2 to the third power, right? And this guy was really 2 to the second power. So then right in here, 2 to the, is it n or is it n minus 1?
N minus 1. So the 4, you had 3 2.
Yeah, that 4 led me to a 2 to the third.
Yeah.
So this, yeah, that n is going to lead me to n minus 1. That formula is way harder to get. And I will say, we had our calendar up here before. Next class, we're going to talk about linear things. That's where you add the same amount every time, like the first example we just did. Then we're going to talk about exponential things. That's where you multiply by the same number over and over again, like we did in this example. Certainly the exponential thing is harder, and I will give you like explicit formulas on that day. And then maybe if somebody remembers, maybe I'll remember, we can come back here and take a look, because there is a formula that you can just kind of plug into and you'll get this as the answer. But I wanted us to kind of feel our way through. It's okay if we're, if that feels like a push, like a stretch a little bit, that's all right. Okay, we talked about the previous sequence where we added the same 1.5 every time. It's called an arithmetic sequence. This has a different name. Lila, can you read the G is? Okay, so if you keep multiplying or dividing by the same number, it's a geometric sequence. This was an example of a geometric sequence. Okay, let's take a look on the next page. So the instructions are written out here, but instead of just reading them, I'll explain the rules of this game to you guys, and then if you need a review, you can check out the rules here. But on your tables, you have a bunch of paper clips and pennies, and then this blank grid. Everybody see it? So what I'd like you to do, I'll draw the grid right up here. We're going to use the smallest grid to start with, and then you guys will use the bigger ones. So what I want you to do is on that smallest grid, put a penny on the far left square, and then put a paper clip on the far right. Okay? Everybody got it? Okay, so here's the goal. The goal is to get the paper clip and the penny to swap places. So I want the penny on the right and the paper clip on the left. But we're going to start here, okay? So here are the rules. You don't get to just swap them. So here are the rules. We are going to move these pieces one space at a time. And the only allowable moves are, you can move from one space into an empty space that's right next door. You can just slide one from one spot to a neighboring spot as long as it's empty. Or just like in checkers, you can jump over one as long as there's an empty space for you to land in, all right? And the last rule is they can't ever go backwards. So the penny is always going to go left the way that I've drawn it here, and the paper clip is always going to move to the right. They can never move backwards. So for example, we could take the penny and do what with it? We could take the penny and move the penny over. So let's go ahead and do that here. So you slide the penny into an adjacent spot. And now there's only one thing we can do because we can't go backwards, so the penny can't go back. We can jump. And so we can take that paper clip and jump it over only because there's an open space to jump into. So there's the paper clip there. And then finally, slide the penny into that adjacent spot. Okay, easy? All right, it's a lot harder once we have more stuff on there. So what you are going to do now is use the next biggest one, and you are going to start with 2 pennies on the left and 2 paper clips on the right. Make sure everybody's got the right starting point here. So in the left, you have 2 pennies. On the right, 2 paper clips. Everybody see it? Okay, so what I'd like you guys to do is pair up. Some of you have 4, well, only one table has 4. Can one of you 3 move over and join Jeremy over here, please? So with your partner, you are going to try to get all these things swapped. Once you've got it, call me over and I'll take a look.